You press Brad.
Yeah. Okay. Thanks, Brad. Yeah, thank you everyone for joining. Here today I'm going to talk about a paper called Where Do Models Go Wrong? Parameter Space Saliency Maps for Explainability. This paper I actually chose because this is a new paradigm shift in the domain of explainability. Traditionally, we have seen many approaches for deep learning model explainability, but most of them are post hoc and most of them are actually focused on input space. That means the data space or the image space, whatever you name it. But this paper is basically turning the attention to the weight space rather than in the input space and trying to find the parameters that are malfunctioning for the explainability. So let's first look at the paper details. This paper actually was presented in 36th New Reps Conference in 2022. And this paper actually received a particular attention and received Best Paper Award for this new approach for the explainability. So the traditional approach of explainability is basically post hoc in nature. In this case, we actually don't know about what the model has learned in advance or in post hoc manner. We just try to see the effects of what the model has actually learned. For example, if our data we consider as X, a d-dimensional vector, and if we say F is our model and FC is the class-specific logic that the model generates, and we try to build a separate explanation model for that. For example, here is our explanation model, and that takes the input and the black box model and generates an explanation for a particular prediction. That means it tries to identify certain regions in the input space that we expect that will make some sense of what the model has learned. Sometimes using these approaches, we have seen that sometimes these input space explanations make sense, sometimes they don't. And research have many studies have already shown that sometimes the model may learn different spurious correlationships. That means sometimes they may not focus on the actual target objects, rather than they may focus on some background or peripheral non-target objects and make the prediction for the target object. But none of the methods actually focused on how we could correct the model. That means they did not focus on model debugging or model correction. They focused on a bit model debugging, that if the model is performing well or not, if the model has learned some spurious correlationship or not, but they did not propose any method to correct the model behavior. Instead, this paper is turning our attention to a completely different direction, that which parameters are actually faulty, which parameters are doing wrong. Let's try to correct those parameters instead. So, if we try to summarize, this paper is actually a paradigm shift for model explainability. That means it is actually a complementary approach to the input space explainability. So, as I told earlier, that conventional saliency maps actually highlight input features to which the network predictions are mostly sensitive. But this work is actually taking a different route. That means it is also considering parameter space saliency and trying to make a relationship between these two spaces, input space and the parameter space. And it is also trying to diagnose the main causes of system failures and how we can recover from such failures for a model without retraining the entire model, just correcting the faulty parameters. Okay, so the highlights of this paper are it identifies and analyzes the network parameters rather than inputs, and it tries to locate the malfunctioning parameters, and then it shows that these parameters are indeed malfunctioning by using some validation approach, similar to what we do for our input space saliency maps. That means it shows that if we turn off these malfunctioning parameters and zero out of these parameters, and then we try to make predictions, then the performance actually improves. Then, in the third point, I'm showing here that fine-tuning a small number of the most salient parameters on a single sample results in error correction on other samples. For example, there is a sample for which this model is making erroneous prediction. And then for that particular sample, these studies identifying which parameters are malfunctioning, and then based on this sample, they are updating the malfunctioning parameters, and then they are showing that fine-tuning on this single sample may make other related predictions accurate. Samples which cause similar parameters to malfunction are semantically similar, and they have also shown that the samples for which similar parameters are malfunctioning are actually semantically similar. And this paper also shows an association between an input space saliency and malfunctioning network components that we will see in later slides. So the key idea is different network filters are responsible for identifying different image properties or different input properties, and mistakes can be understood by identifying erroneous filters and network parameters. So these are all of the hypotheses the authors actually made, that different filters are responsible for different functionalities, and mistakes can be understood and can also be corrected by identifying erroneous filters and correcting the erroneous filters. And for this correction, they actually use gradient information for the loss function as a measure of parameter sensitivity. That means they did not use in traditional input space saliency, we usually use logic value or the prediction value, prediction probability, to identify the salient regions in the input space. Indeed, they are assuming that for the training data, if the model converts correctly during the training time, the loss should be approximately equal to 0. So now to correct the model or to identify the erroneous filter, they are picking a particular sample, they are passing the sample through the model, generating loss, and they are calculating gradients of the loss with respect to all of the parameters. So now let's talk about parameter saliency profile. That means how can we identify that which parameters are actually faulty, which parameters are malfunctioning. So likewise, as I was saying in the last slide, that we have sample X for which the model is making a wrong prediction. Let's pass it, calculate the loss, and then take the gradients with respect to all of the parameters. So let's name it S of X, Y, I. I is the index for a particular parameter. And then as these parameters will be evaluated based on filters, that means a filter might have several parameters, but for the profile evaluation or for the creation of saliency profile, they are actually treating each filter as a single entity. So for assigning a particular saliency value to a filter, they are actually summing all of the absolute values. They are actually averaging the gradients of each filter. For example, here we are showing the saliency value for the cake filter. And alpha k is the set of parameters of that filter, including bias value. Okay, so here we are showing a ResNet 50 filter-wise saliency profile. That means the saliency profile we just described, averaged over samples in ImageNet validation set. And the saliency profile here we are showing have been sorted in descending order. So from the saliency profile, we see that the shallow layers, that means the early layers, have higher saliency values compared to the later layers.
What is the input?
Second,
What is the input?
input, image. Input is the image.
Where? 30, 55, or
No, it is not the image. It is the layer ID. It is the layer ID of the ResNet 50 network.
Where is the input layer? Input layer.
Input layer is 0, early layers. It is showing from early layers to deeper layers. And for each layer, there might have number of filters, say 50 or 60 filters. And all of them have a saliency value for each filter. And all of the saliency values are sorted in descending order for each layer. And they are showing in equal width space on the x-axis.
Thank you.
So here, their observation is that early layers filters have higher saliency values compared to lower, deeper layers filters. Because early layer filters are responsible for capturing low-level features like textures, colors, that sort of things. And whereas deeper layers are mostly responsible for creating semantic meaning in the input. Okay, so typical networks have fewer filters in, so they have, their observation is that why earlier layers have higher saliency values. So they're saying early filters input low level features that I just talked about. And typical networks have fewer filters. There could be another reason that usually lower level filters have few number of filters than the deeper layers. And the effects of early filters may cascade through the other layers. So they might have some cumulative effect for the entire network. Okay, so they did some standardization on the saliency profile. So let's name it standardized saliency profile. So here they are showing that for the same network, the filter-wise saliency profiles have been standardized. And they are separately showing the average saliency profile for correctly predicted samples and incorrectly classified samples. So their observation is that for correctly classified samples, usually the early layers filters have higher saliency values, but for incorrectly classified samples, later layers, deeper layers filters have higher saliency values. Sorry. Can I hide this one?
Yeah, click on the chat. And then close it.
Okay, so input space saliency. So how we can identify those fixed cells in the input space which are responsible for these malfunctioning parameters. So what they did is they actually, first of all, they decided which salient filters they want to explore. Let's name it, for example, a set of filters F. It may have 10 filters, 20 filters, or 50 filters. Then they tried to boosted the saliency profile, the original saliency profile. That means they tried to boost these filters. For example, if a filter is outside of this set, they did not change the saliency values. But if this filter belongs to this chosen set of filters, then they boosted this saliency value. And then this is the original standardized saliency profile, and this is the boosted saliency profile. Then they measured cosine distance and calculate the gradient of this cosine distance with respect to the input x. So what they're trying to do is, that means if someone wants to boost these particular filters, which pixels in the input space will be more sensitive? We are trying to calculate that. Sorry. Okay. Okay. So for validation purpose, they are using actually two data sets, CIFAR10. Sorry, there's a typo here. CIFAR10 and ImageNet data set, and they are considering two models, ResNet 18, ResNet 50, both are pre-trained. And for the validation of these malfunctioning parameters, they are what they are trying to do is they are zeroing out the filter weights, the malfunctioning filter weights, and the corresponding bias values, and the associated batch normalization layers, so that they are ensuring that the corresponding feature map for the next layer will be 0. And then they are observing change in the incorrect class confidence, the change in the true class confidence, and the percentage of the samples that flip their label to the correct class. Finally, they are comparing the most salient against the random and least salient features. We will see in the results section. Okay. So the first one is incorrect class confidence. So when they are zeroing out the malfunctioning parameters, and then they are using three metrics. The first matrix is incorrect class confidence. So ideally, if they want to validate that those are the malfunctioning parameters, so ideally the confidence of the incorrect class should decrease. So they are showing in the first panel, in the panel A, they are showing that if they zero out those malfunctioning parameters, the incorrect class confidence actually lowers, decreases. In the second one, they are showing that the correct class prediction increases. Okay. And the third one, percentage of corrected samples. Okay. So when they zero out those malfunctioning parameters, for some previously wrongly classified samples, model starts to make correct predictions for them. Here they are showing that how, based on the saliency profile, parameter saliency profile, if they clusters images, based on the similarity of the parameter saliency space, they see that the nearest neighbors are actually semantically similar. Okay, so here they are showing a quite a bit different experiments for these nearest neighbors. So they are showing how these nearest neighbors actually change if they consider only early layers filters or only deep layer filters. So they are showing here, for example, in the first row nearest neighbors are based on early layer filters, and the bottom row nearest neighbors are actually based on deep layer filters. So they are showing that the early layer nearest neighbors are basically based on color, contrast, histogram, that sort of things. But the bottom layer nearest neighbors are actually based on their semantic similarity with the input. Now they are showing a very interesting experiment. That means they are just fine-tuning on a single image to correct those malfunctioning parameters.
Can you explain again, like, what?
The
So
earlier
I take an image. The image is misclassified.
Mhm.
I take the saliency with respect to the correct class. Right?
For what?
For
No,
this whole work.
So parameter space saliency is different than input space saliency. So parameter space
Still the grade.
gradient, but
With respect to what?
with respect to weight.
Yeah, but we compute it for free when we do saliency.
Yeah, we did.
What gradient of what? Okay.
Gradient of loss.
So loss, you
Not
don't
the
put like
logic
the
value.
entire loss or logic value or loss.
Loss.
Okay, so you take the loss and you are saying,
Loss for a single subject. Yes.
yeah, for that subject, you know you know the answer, you know this is a wrong prediction. You take the
Yes.
gradient of loss, and so the gradient, the higher the gradient, what does that mean? The higher the gradient of this parameter, or they don't look at parameter, they look at the filter entirely, right? They
Yeah.
look at the entire filter.
Filter. They actually they took absolute values of the gradients first, and they averaged over each filter.
Yeah, they're taking a filter as a separate component in this layer.
Yes. So for each filter, they actually generated one value, one scalar
But by averaging all the values of the
of the
whole
parameters within the filter.
Yes.
Yeah, the gradient. So
Mhm.
it's okay. It's the filter based gradient.
Yes.
So their hypothesis is, if it was a training sample, then ideally, if the model was model conversed correctly, the loss should be zero. There should not be very sensitive to the parameters. But for this wrong prediction, the gradient of the parameters with respect to the loss, there should be some sensitivity.
Well, the gradient of the loss with respect to this parameter, just a small correction. But okay, so this is the gradient that says
Higher
Okay,
the
we-
sensitivity,
reduce that parameter to make the loss even lower.
Yeah.
And reduce that parameter, they're like, oh, we'll just turn it off. We'll just reduce that parameter to zero, basically, right? We will zero out this. That's the logic, right?
that's the validation technique. That's not the fine tuning. Fine tuning is different. So for the validation, they did is they first identified those malfunctioning filters.
Mhm.
They did not calculate gradient step update. They did not do it. So what they did is they just zero out those malfunctioning parameters, and they checked for predictions on some related samples.
Yeah, but when they improving the quality, it's like,
Okay, so we will discuss that improvement.
no, I'm still on the 3 slides back, so
Okay.
I don't know how can I.
Oh,
So
this
the-
one is the validation. This is no gradient update at all.
So here they zero out the filters
Mhm.
which have non-zero gradients with respect to loss
Not all
on the
filters.
incorrect prediction.
They decided, for example, we will work on 10 most malfunctioning filters.
Well,
First of all, they
the
decided.
highest gradient norm,
Yeah.
basically, and they zeroed them out, and the prediction improved on other samples. They only looked at the incorrect samples.
Yes.
But it improved on other samples in the training set.
Yeah.
This is training set.
Yeah, incorrect class confidence change. That means it changes the incorrect class confidence. And they also tested for true plus confidence actually increased, actual target score increased,
Mhm.
and percentage of correct samples. Corrected samples, okay. So for example, for 50 samples, the model was making wrong corrections. Now, out of them, 12% of those 50 samples are now making correct.
Yeah, I'm trying to,
corrections.
this one is on the surface clear, like I'm trying to figure out what are they doing with the model? And so what you're saying is, okay, they're looking at the filters with high gradient and zero them out.
Mhm.
And they are not looking at, but then you went into the cosine distance of this gradient and the gradient of what?
Yeah, cosine distance is basically focusing on, okay, so still we are talking about the parameter space. We are not talking about the input space. So cosine distance comes into the play when we consider corresponding input space segments. Okay, so which pixels are driving or associated with these malfunctioning parameters? Then the cosine distance comes into the play.
And what does it do exactly? So it tells us like which parameters within the model, like which parameters are malfunctioning because of that. What exactly does it signify?
Actually, we are not still up to that point. We
Okay.
have slides.
Okay,
later.
let's
Yeah.
go on.
Yeah. So up to this point, they have identified malfunctioning parameters, and they are showing that they are indeed malfunctioning. Because if we zero them out, the performance improves.
Without the training, right?
Without training, without any gradient update step. Okay. And they are showing that the nearest neighbors in the parameter saliency profile are semantically similar. That means for some samples for which if the malfunctioning parameters are similar, the input samples are semantically similar. Okay, here they are trying to improve the model based on a single sample. For example, for a particular sample, the model is making wrong prediction, and they have identified some malfunctioning filters for that prediction, and for that single image, they are conducting a gradient update step. And now they are showing that only updating for that single sample improves the classification performance for the nearest neighbor samples. That is what they are showing. Any question at this point?
I have a question.
Yeah.
So how I'm interpreting this is like, let's say you have a cluster of on the previous in the previous slide you showed us few pictures of dogs or humans, right? So like for this particular human being, I have particular this dog, I have like a whole cluster, and then from that cluster I'm basically picking up a single sample, and then I'm correcting it, and then
You are actually not correcting it. What you are doing is you are taking an input sample for which you know that the model made the wrong prediction.
Yeah, okay.
So your first task is to calculate the saliency profile for this sample. So you first of all you calculate the saliency profile. You identify the most malfunctioning filters, and you want to improve those filters. So you are updating the gradient information of those malfunctioning filters for that particular sample only, and forget about that sample. Now you already calculated all of the nearest neighbors of that sample. For example, 50 nearest neighbors, right? Now you run the updated model on those 50 nearest neighbor samples and evaluate the model's performance. For all of these nearest neighbors for which the model predicted wrongly earlier. Now you calculate how many wrongly classified samples are now being correctly classified.
Okay, got it, got it.
That is what they are doing here. So, for example, in panel A, percentage of misclassified samples corrected after fine tuning. So they are showing here, for example, the dotted line, it's the fine tuning over the entire network. So they are showing that only updating 150 filters, it is less than 1% of the ResNet 50 network, 0.6%, 0.6%. So only updating 150 filters, that means less than 1% parameters of the network may be sufficient to get the equal performance of the fine tuning of the entire network. That is the result of the first panel. And in the second panel, they are showing average percentage of corrected neighbors. That is what we are just talking about. That means how many wrongly misclassified neighbors are now being correctly classified. And for the third panel, they are showing true class confidence change in neighbors. Okay. So what percentage in confidence is for actually changed? Now we will talk about the input space saliency maps that you were talking about, right? So they calculated the saliency profile, and then they boosted some malfunctioning parameters, computed the distance, cosine distance, and based on those cosine distance, they actually trying to identify the input region which are responsible for that boosting. That means which pixels in the input space are actually driving those malfunctioning parameters, malfunctioning filters. So they identified some input pixels for 10 most salient filters. Here they are actually naming it a bit differently. In traditional post-hoc interpretability, we call it salient features to mean it that these pixels are driving for the prediction. But in this word, they call it salient pixels or salient parameters. By this, they are meaning that these parameters are responsible for misclassification, not for the correct prediction. That is completely in the opposite sense. Okay, so as we can see that this image was actually the correct class was great white shark, but this sample was wrongly classified as killer whale. And they have identified 10 most salient filters, that means malfunctioning filters. And based on the cosine distance, they calculated those pixels which are driving those 10 malfunctioning filters. So as we can see that they are actually relating, that means those malfunctioning parameters are actually related to boat and the sail. So they conducted an experiment that what happens if they mask out these salient regions in the input space. For example, as you can see, the panel A is reference image misclassified as killer whale, and B is the input space saliency visualization, as we have already talked about. Pixels that cause the top 10 salient filters to have high saliency. And then the panel C is showing the change in saliency values of the erroneous filters across masking experiments. That means if we use only mask one is here the seal only, and mask 2 is boat and seal, And mask 3 is actually the extended mask, as we can see. For the first mask, they are actually only masking out the seal. And for this experiment, they are masking out seal and the boat. And for this experiment, they are actually masking out boat seal and other extended resin based on this input.
Are they doing this manually checking, like, for this experimentation, they're manually putting the mask on the image and then checking if it gives the proper salient features in this case?
I don't think so. They actually masking out based on the magnitudes of the saliency values. I think so.
Are they thresholding those?
I think so.
Okay.
Do they zero out the image and run the image back through the network?
I think based on the structure here, we see what I assume they did not provide exact information, but I think they actually replaced those areas with the image average.
Can you press like space or something on the keyboard? No, okay, that's some. Well, I think it's there, yeah, the top one.
This one is what? TV.
Can you press it?
Yeah, one thought that I had.
Okay,
when I was
okay,
reading-
it go.
One thought that I had when I was reading the paper is that like.
Okay,
when
so.
they replace it, it makes a big difference.
So what happens? The result is in the actually in the C panel, saliency values change of the most erroneous filters across masking experiments. So if we just mask out the seal, the saliency values for the malfunctioning filters actually drop. And if we mask out seal and the both, then the saliency values for the corresponding filters drop more.
I mean, it's hard to tell visually, but it looks like some of the pixels, a lot of the pixels in the shark are contributing to the saliency. And I wonder, like, why didn't they mask those out? A lot of those look as the salient as.
Your assumption may be correct. Maybe they,
It looks progressive from D, E to F, that's the only guess, but it's still a short.
I'm not sure that they did it entirely based on saliency thresholding or they manually did it, I'm not sure. But based on, because saliency values can be a bit random, it may not be fully structured, as you have guessed, that there are some salient pixels in the shark patch.
But there is another possibility is because of interrelation of all the filters. When you do the first mask, you have to recompute that again with the first mask, and it will change. Maybe the sharp overlapping pixels will disappear after you put the first square, or it's not like a linear thing. It depends on the user. It changes with the. So progressively, but masking, you changing what to do next.
I see.
Yeah, but the extended mask, for example, the extended mask is actually not hiding any pixels of the shark. So it seems they are doing it manual. They are not doing based on some automated way, like based on saliency thresholding. They're not doing it like that way, I think. They're using some bounding box information for non-target objects, I
That makes
think.
more sense. That makes more sense, because even when you, like, for example, if I take another case here, when you do segmentation of any images, right, you definitely take the object of that image. So in this case, if I take the object as the created by sharks and the human being, and also the information of the incorrect salient gradients in this case, then it makes more sense, because then I will get a better accuracy in that case, because I'll basically just be masking all the incorrect gradients, and I also know the object information. So I guess that experiment that does make sense, but it would make, I mean, it would be more impressive if they would have tried to do it through a more automated fashion rather than.
Yeah, I think so, because I did not get accurate information within the main parts of the paper. Maybe
I know, that's
there
just
could
my
be
view,
some
I'm
details
not
in the
sure.
appendix, I'm not sure. But as it is understandable, maybe they are not doing it using some automated approach because some pixels, some salient pixels are within the shark area, right? Okay, so, oh, we are almost done. So they are now showing what kinds of mistakes usually a network makes. For example, all of the presented images are misclassified by ResNet 50. And the correct class level is specified in the top row. That means, for example, pizza is the correct class level and the bell pepper is the predicted class, right? Okay, so for example, for A and B, the target object is confused with another object in the image. So for example, the label is for pizza, but the image contains a bell pepper, right? So the model actually was confused and decided positively or affirmatively for the bell pepper, right? And for this one, for the third one, the correct class is leopard, but the actual true level is sorry, the predicted level is jaguar. So they have semantic similarity, right? The salient pixels are focused on the target object features, which confuse the network. And for the D, background features confuse the network. I did not understand how background features actually confuse the network.
It's like everything is background.
I think, I mean,
Everything,
And
But-
Texture,
but-
maybe texture. Maybe that's what they mean is
I
texture.
think that's kind of why attention is so useful. It basically trains the network to only focus on salient stuff.
no, house finch is actually another kind of bot. And Janku is another kind of bird. Okay, so they are misclassifying Janku as house finch. But I did not understand why how background features actually confuse the network.
Well, this is a classical clever hands example.
Right.
Train a classifier to recognize American tanks from Soviet tanks, and then later perfectly, and then later realize, oh, all Soviet tanks are like at night, and all American tanks are bright daylight, like.
Okay,
of course, so.
So
background
you mean
features.
that this background is more aligned to house
Yeah,
finch?
maybe the other, like, maybe this bird doesn't live in the desert and the other one lives in the desert. And now this bird happened to be on the desert scenery and it's like, I don't know what that is, but it's desert, so it must be a finch. And of course, there is no reasoning at all, but it's just.
Yeah,
argument.
I got it. And for the last one, the correct class level is passenger car, but the network prediction is locomotive. And as the author,
What's the label that the network said? Sorry.
it's locomotive.
Locomotive. Yeah, that's what I think.
Yeah, so so it is, the authors are saying that the model is more accurate than the actual annotation. In this case, the labels are noisy in this.
Reminds me of Piaget,
Yeah.
the like when we don't know when we don't know what kids don't know. It's like we don't know anything what's in kids' head, and kids don't know what's in our head, and we're trying to evaluate kids, are they smart or able to understand? And the kids are like, in this example with pizza, which class? And the kid is looking at the parent is like, pizza? And the parent is like, yeah, pizza. And like next kid looking at the parent is like, bell pepper, yeah, bell pepper. Okay, well, then the parent goes, writes an article. The kids don't understand physics, but the kids are just don't know what do they want from them.
So basically, we are done. At this point, if you have question, I have just one more observation that I am convinced that those malfunctioning parameters are responsible for some misclassification. But from the validation experiments they conducted, I have observed that zeroing out other kinds of filters also improved accuracy. So my question is, if these malfunctioning parameters are only responsible for this misclassification, turning off other filters would not increase the model prediction.
We should go back to the classics, Jan LeCun's optimal brain damage.
For example, this one. If you see this line. Okay, so zeroing out a random filters.
But they don't correct the field.
Okay, sorry. List setting. This is the list setting. Let's take an example of random zeroing out. So, for example, it is random zeroing out. That means they are zeroing out some random similar number of filters, not based on saliency profile. So, still, the confidence score of the incorrect class is decreasing. Why? This is my question to the audience.
Yeah, optimal brain damage, 1995. I don't know what year paper. It's when we knew all of that. Right? Sparsity induces performance until everything collapses.
Mahfuz, I have a question.
Yeah, again, I have a very basic question. So they only zero out the gradients, they don't correct the gradients, right? They don't, so,
Oh, it's 89. The optimal brain damage paper is 1989.
Okay.
40 years.
yeah, so they just turn off the gradients, as you said. In
For what?
this case, what are they turning, what are they making zero in this case?
So the weights have values, right?
Yeah,
Weights means their values, right? So what they did is they actually replaced those values by zero.
right, so, and what happens in a classical network, you don't zero them out, you basically try to correct them so that they make an accurate prediction. So you change the values of those weights so that they make a correct prediction, right? So my question is, like, even if you zero out the weights, I mean, yeah, I mean, you can zero out the weights to give you the correct prediction for that particular class, but that should not happen for all the classes in the data set. Am I wrong in that?
Yeah. Because those filters are responsible for only misclassification of those particular class samples. So zeroing out those filters, they are just verifying if these improve the classification accuracy for those semantically similar samples.
But it's been trained on kind of a variety of samples, right? So I'm kind of interested to see what effect that would have on classification performance for other kinds of samples as well. It seems like you just zero out those parameters.
Maybe you have seen this panel A. This panel A, as a guess, it is not only for the nearest neighbors, it is for the entire network. From the validation set, they take one misclassified sample each time, identified 150 or let's say 50 malfunctioning filters. They updated the gradients of those malfunctioning filters based on only that sample. Then they repeated over the entire validation set for all the misclassified samples. And they are showing here the overall classification performance percentage of corrected samples. Yes, they are showing that Okay. Percentage of corrected sample. Okay. They are showing that all of the misclassified samples, if they correct 150 filters in this manner, then all of the misclassified samples will now be predicted correctly.
Oh.
I think it is not based on the nearest neighbors. It is based on all of the misclassified samples. And for the panel B and C, they are evaluating based on the nearest neighbors.
Okay, thank you, Mahfuz. Maybe you can continue the discussion if there is a question
Yeah,
here,
sure.
and online discussion can be done in Slack.
Mhm.
But I have another Zoom meeting that
Yeah,
I need my Zoom back. And please put,
Yeah, thank
put
you,
your
everyone.
slides
Thank you.
online. I will put the recording. Thanks so much. Yeah.